All right, number 21, and this is the first of our fluid dynamics problems, moving fluids. And so what do we have here? We have a tube, a cross-section, a pipe, something like that. We've got water flowing through here. Actually, it doesn't specify which direction the water is flowing. It's not actually important to us. There are going to be no air pockets inside here. Okay, so it's completely filled. The water is flowing either, could be being pushed up or it could be being pushed down here. Anyway, there's going to be a couple of steps that we need to consider here. And the first one is actually what we call the continuity equation involving the flow rate. That means the volume of water per second, say, moving through this section of the tube must be the same volume per second, the same amount of liters per second moving through that section. And so our continuity equation looked something like this. And what do all these symbols represent here? So A1 and A2, you used 1 and 2. So I'll tell you what, if we want to, we can label A as 0.1 and B as 0.2 here. So A1 is this cross-sectional area, all right? And I guess in my picture, I'm kind of assuming it to be a cylindrical type tube. And so A2 would be the cross-sectional area of that. Now, we don't have to think too hard about this because it just gives us those two cross-sectional areas. It says that cross-sectional area 1 at point A, here it is, 0.06, and the cross-sectional area at the second point is 0.03. It's half as large. What do V1 and V2 represent? V1 and V2 represent the speed that the fluid is moving at, and we're also given V1. So actually we have 3 out of these 4 quantities. So this would be our red here. The speed of the fluid at point A times the speed of the fluid at point B. And so it should be not too difficult for us that since the cross-sectional area is half as large here, doesn't really look like it in my picture, half as large, then the speed should be twice as big. And so the speed of my fluid at point B, point 2, should be 6 meters per second. And so we're going to use that information in just a moment. And I'll tell you what, let's hang on to that. I'm going to need some space, so let me just redraw that here. 6 meters per second, and the speed here, we'll just include those in our picture. The result, I'm going to clear myself some room here. And because the next concept that we're going to use here is Bernoullis equation. And what do we have here? We have point A and point B they're 2 points in this connected fluid, and there's some relationship between the pressure, the height, and the fluid speed at those points. So there's kind of a big equation here. Let's just write the whole thing out. And again, I'm just using points 1 and 2 instead of A and B. So 2. Whew. 6 terms. It looks a little intimidating, don't worry too much. There is one other thing we're going to need to do here, and that is that we've got this y1 and y2. These represent the height at points A and point B. And, well, we have to define where is the height 0. And I usually I look at the 2 points I'm considering, and whichever one's lower, I make that the height 0. Just say y equals 0 here. And so we can see that based on that definition, this height is going to be 0. In fact, I guess we can start filling in a little bit of information here. This height is going to be 0. A little bit more room on this side. All right, height 1 is 0, and this last term over here well, I will plug it in later, but this height is going to be 2 meters. I can see that from my picture. So what other information can we plug in here? Well, we do have a bit. We have our pressure at point 1. I guess we can plug in some numbers here. What's the density of our fluid here? We're considering this, should say water here. Water has a density of 1,000. And the speed of the fluid at point A is 3 meters per second. So we're going to square that. Over here, we've got the pressure at our point 2. And similarly, the density of water, the speed at point 2, which we found out is 6 meters per second. And we've got that one more term here, the density of water times g and times the height at point 2, which is 2 meters. And so at this point we can start plugging in some numbers. What do we have here? Let's see, this is going to be 4,500. And this is going to be 18,000. And this term will be 20,000. And so let's try to simplify just a little bit more. Let's subtract the 4,500 from both sides. And what am I going to get here? I'm going to have 33,500. And in our standard units, what is the standard unit for pressure? We can call it the Newton per meter squared, which is also called the Pascal. All right, so I can write this if I wanted to as Pascals. And now I did have answers here in kilopascals. So put it this way: 33,500 pascals equals how many? It's 33.5 kilopascals. Okay, because kilo means 1,000. I move this over 3 times. And so, what do we know? What else is given? The last piece of information here. It tells us the gauge pressure at point A is 50 kilopascals. The gauge pressure. Now this P1 by itself represents the pressure or absolute pressure. All right, and so if the gauge pressure is 50 kilopascals, we could write this as, well, 1 atmosphere plus 50 kilopascals. Okay, yeah, because our gauge pressure means the pressure above 1 atmosphere. So similarly, for pressure 2, I could write this as 1 atmosphere plus the gauge pressure at point 2 gauge pressure is the pressure at point 2 equals 1 atmosphere plus the gauge pressure. I can subtract 1 atmosphere from both sides, and then I could subtract 33.5 kilopascals from both sides. And that would give me answer A here, 16.5 kilopascals.